Today I'm going to be talking specifically about droughts, so the extreme lack of moisture. The water cycle is, a little bit more complicated than when we're talking about temperature. The temperature just gets warmer, but it's not so direct in terms of what the water cycle does under climate change. And that's important because the water cycle may actually, be a lot more important for human and natural systems than temperature by itself. And so I showed this diagram of just reminding us, all of the places that water's important. Like it's important for the snowpack and using that as a natural reservoir for water for people and for ecosystems. Important for a lot of industry, manufacturing. We use it in waste treatment. We use it in energy production, so not just hydropower, but like all of our power plants essentially boil water, and so you need a lot of water available for power plants. Drinking water, of course. And then agriculture is a big one, both the water that's available underground for irrigation, as well as just the water falling as precipitation on agriculture. I also showed you this graph that's global drought. In this case, it's the percent of the land area under extreme, severe, and moderate drought, according to this measure called the Palmer Drought Severity Index. And I showed this to kind of emphasize again that it's more complicated than temperature. It's not, you don't see some hockey stick, and in fact, you don't really see any trends in global drought. And a lot of that has to do with different regions changing in different directions. And a lot of it has to do with just the fact that we're going to be talking about today of how precipitation changes as it gets warmer, and precipitation tends to increase as it gets warmer. So today, our class learning outcomes are these three things. I want you to understand, I'm going to introduce a couple more terms here. Understand the difference between a meteorological drought, and there's these two other kinds of droughts, hydrological, agricultural droughts, that I'm going to kind of put in the same bin. So kind of two major kinds of droughts, either a meteorological drought or a hydrological agricultural drought. So what's the difference between those two? Understand why hydrological agricultural droughts should increase more than meteorological droughts as the climate warms. And then understand the contribution from increasing greenhouse gas concentrations to the current mega drought over the United States Southwest. So in one of your readings about what causes droughts, that one talked about what a mega drought is. And that's a drought that lasts a very long time, more than 2 decades, is sometimes called a mega drought. So the mega, in terms of the mega prefix, is referring to time, not necessarily intensity. So long time, 2 decades is a very long time to be in a drought situation. And they also talk about, in this reading, some of the major themes that I'm going to be talking about today. In a warmer world, evaporation increases, which can make even wet regions more susceptible to drought. So that's going to be a major theme. And then here is our different categories of drought. Droughts are divided into different categories based on where in the water cycle the moisture deficit occurs. Meteorological drought has to do with precipitation, so a lack of precipitation. Hydrological drought has to do with basically water on the ground, so runoff, stream flow, reservoir storage, so water that's on the ground. And then agricultural drought has to do with water on the ground, so that's why I kind of put those in the same category. So agricultural, or they also call it ecological drought, is something to do with the land not having very much moisture in it. So the meteorological drought is going to have to do with precipitation, the amount of water coming in from the top. And then these other kinds of droughts are going to have to do with just how much water is there in the ground. Okay, so we are going to be talking about, we're kind of going to lead to what's going on in the Southwest US right now. And this is a headline from LA Times, a front page, climate on the front page here. The Western mega drought is the worst in a millennium. And study says it's being driven by climate change. And so this is the study that just came out in Nature Climate Change, which is one of our premier journals in climate science. And so we are going to be looking at the results of this study in the context of some of the physics that we're going to be talking about today. So first, I just want to take a step back and go look at the water cycle in a little bit more detail. And we're going to look at kind of the basic theory of the water cycle and how it should change as it gets warmer. So I'm going to do my third diagram like this. So if you remember, I spent a long time on this particular diagram, which was looking at radiation flows in and out of the Earth. So these arrows were electromagnetic radiation, shortwave radiation, and longwave radiation. And I also applied this to flows of carbon. We talked about the carbon cycle, so flows of carbon in and out of reservoirs. So we're, here we have flows of energy, joules per second per meter squared. And here we have flows of carbon, gigatons of carbon per year. And so this will be my third and final version of that. And this will just be the water cycle. So we're going to be talking about flows of water molecules, flows of H2O. So here's our H2O down here. So if you remember from, 6th grade or something, when you first learned about the water cycle, we have the sun coming in, the energy from the sun, and we have this, we have liquid water in the ocean, and the energy from the sun, the radiation, breaks these hydrogen bonds that the water molecules use to kind of hug each other, and causes evaporation, right? So the sun starts it off, and we have evaporation, and then what's next in our water cycle? So it goes up in the atmosphere, gets colder, and what happens? Condensation. So first you're going to get a cloud. So that's just going. So we have liquid form down here, then it's in gaseous form, so water vapor, and then condenses into clouds. So then we're back into liquid or ice form, and then we've got precipitation. So those are our three things, right? Evaporation, condensation, precipitation. And all of our water on the land comes basically from the ocean. Right, so we have evaporation over the ocean, and then we have advection or movement of that water over the land because the atmosphere is moving it over the land. And so then we have precipitation over the land. And you may not think about this too often, but all of that water that you see on the land, no matter if it's in lakes or rivers or glaciers, basically at some point was in the ocean and evaporated and was advected over the land. And then we also have evaporation over the land. Okay, so precipitation, just another excuse to show this animation, which I really like. I think this is the third or fourth time I've shown it, but just to remind you, this is kind of the climatology of what precipitation looks like going through the year. So here's our months up here, and you can kind of see the seasonal cycle where this intertropical convergence zone, this is where the most thunderstorms are, right at the equator. It kind of follows the sun. And so for this class, kind of the important thing to notice about this is just the general pattern of you have the most precipitation near the equator, and then you have these subtropical dry zones where all of the world's big deserts are, off of the equator here. So Sahara is the biggest example, and then Middle East, and the South Asian monsoon, June, July, August. So it's looking at it from this perspective, it's almost just like India gets into the intertropical convergence zone, and you can see that it's enhanced because India is land and surrounded by water. But yeah, I mean, just huge seasonality in precipitation. So that's the monsoon there. And you also might notice that, like, let's say June, July, August, September. If you look up here, you get more precipitation at these high latitudes when it's warmer, so in the summer. So that's relevant to climate change because it's getting warmer. So this is our baseline water cycle. But what about the water cycle under global warming? Okay, so one thing that's really important to point out before we get to that is this very important fact that I'm not sure if I've talked about very much in this class, but it's that the land warms faster than the ocean as we put more greenhouse gases into the atmosphere. And so this is a map kind of showing that. This is climate models, but we can see it in observations as well. This is the ratio of local warming to global warming. So it's like how much has it warmed locally divided by how much the globe has warmed. And so that means if this number on top is larger than the number on the bottom, then you have a number larger than 1. So anything to the right of 1 here is a location that's warming faster than the global average temperature. So we can see that on land, most of those colors are over here. So they're above 1, meaning that they're warming faster than the global average. And so if you kind of just look over land in general, it's about 1.5. So it's about 50% faster warming on land than over the ocean. Okay, so what happens to the water cycle as it gets warmer? So you might just be able to intuitively think about if it gets warmer, so that we have, let's say, 1 degree of warming over the ocean, and now we're going to say 50% more warming over land, so 1.5 degrees warming over land. What happens to evaporation? So this 1 over the ocean increases. And it increases not too dramatically. It's 3%. You get 3% more evaporation per 1 degree of warming. So this goes, I'm just trying to illustrate this arrow gets bigger. So 3% increase in evaporation. Now I'll come back to this. This becomes important for thinking about extreme precipitation, which I'll talk about next time. But the atmospheric reservoir of moisture, reservoir meaning like how much it can hold, that increases at 7% per degree Celsius of warming. So kind of we have more, our clouds can be kind of bigger. We can have more water in our clouds. We kind of will just ignore that for today. Okay, so if evaporation increases by 3%, then precipitation must also increase by about 3%, because whatever's going in is coming out. We're not just going to evaporate the ocean into the atmosphere and have it fill up. We're going to just increase what's going in, and that's going to increase what's coming out. So increasing precipitation by 3%. And so this is where, immediately it's like, okay, droughts are going to be inhibited in some locations because globally precipitation is going to increase as it gets warmer. So I have increase of 3% here in our precipitation. And then we're also going to have more, we're going to have like 3% more water going over the land, because just kind of this whole thing increases by about 3% per degree Celsius of warming. So then over land, about 3% more precipitation. Then we're going to have like 3% more runoff. Okay, so here's the critical thing. It's like the most important point today. We got 1 degree of warming over here. We got 1.5 degrees of warming over here. We have a 3% increase in evaporation. That means 3% more water over land, 3% more precipitation over land. But the land warming faster than the ocean means that evaporation over the land is going to increase in accordance to how much warmer it is over land, not how much warmer it is over the ocean. So evaporation over land is going to increase by more than 3%. So I said that evaporation increases by 3% per degree of warming. And so it's 3% over here for 1 degree of warming over here. But it's 1.5 degrees of warming on land. So that means evaporation increases by 4.5% over land. But our precipitation is basically coming from the ocean. It's coming from this evaporation component. So our precipitation only increases by 3%. So we have a mismatch here. We have a situation where over land, in general, evaporation increases more than precipitation. So why does precipitation over land increase by 3% per degree? Because evaporation over the ocean increases by 3% per degree. And so that's that, pathway. Then why does evaporation over land increase by 4.5%? Because it's still increasing at 3% per degree, but it's the land warms faster than the ocean. And so you're getting more evaporation increase over land. And so then this imbalance means that you are going to be drying out the land. So we have, the way I've drawn it in general, the land dries despite an increase in precipitation. So you can have your rain gauge there and showing that your precipitation is increasing, but still have your crops be more stressed than what it was previously because of this evaporation increase. Okay, so let's look at that a little bit in space. This is using climate models to look at these. So we're going to look at each of these components: the precipitation, the evaporation, and the moisture in the land, which we usually measure as soil moisture. So first, precipitation. This is a map now, not of precipitation in the regular climate state, but precipitation change. So does it get wetter with warming? So this is in 2100 under high emissions in 39 climate models. Does it get wetter? Do you have more precipitation with warming? That's the greens. Or do you have less precipitation with warming? That's the browns. So these can be negative because you're not talking about actual precipitation, you're talking about changes in precipitation. We can see the general pattern here. If we go back to just the way that precipitation is distributed in the current climate, in the baseline state, the pattern of change looks very much like the just climatological pattern, right? It's like wet at the equator, dry, and then wet again at the higher latitudes. And so we get this change that looks like that. So one phrase that's used a lot in climate science is the wet get wetter and the dry get drier. And this is one kind of application of that. There's another application that I'll talk about next time, but this is one that where it is already dry now, it gets drier, you get less precipitation. And where it's already wet now, it gets wetter, you get more precipitation. And so what I just showed is that on average, precipitation increases over land, and you can still get drying of the land even with that increase in precipitation. But you can imagine if you're at a location that also has a decrease in precipitation, then you have this like double whammy where you have the increase in evaporation and a decrease in precipitation. And so both of those are going to combine to make it so that you have a drier land surface. And so the Mediterranean region is a location like that in Mexico, and parts of the Amazon, South Africa, parts of Australia are those locations that would be hit on both sides of the input and the output of water. And so that's why in your reading, they have this diagram that looks like that. This is, you know, the regions where drought is expected to increase the most. And the pattern is very similar to that precipitation change pattern. But these are the locations where we can kind of be most sure that there's going to be more water scarcity as it gets warmer. Okay, and then here is evaporation changes with warming. So this is the same type of graph. This is in 2100 under high emissions, average of 37 different climate models, and evaporation change, where positive is up here. So over most land surfaces, you get an increase in evaporation. And these locations where you don't see an increase in evaporation, that's only because they're so dry that there's not water to evaporate anymore. So over kind of all land surfaces, you have an increase in the propensity of water to evaporate from the surface into the atmosphere. So it's kind of like the precipitation pattern change is pretty regional. There's quite a bit of difference, but evaporation is more universal, kind of everywhere evaporation increases. And so if you kind of put these together then and look at soil moisture changes, that's just how we tend to quantify the amount of water in the land. That's what that looks like. So where it is reds and browns, that's where you get decreases in local water available for, you know, all of its uses basically. So we care much more about just the water that's at the surface of the planet, more so than just thinking about like the input from precipitation, where that's just one component of our hydrological budget locally. So kind of all of the United States focused on the US Southwest. We have kind of all of the Amazon, all of the Mediterranean, all of basically Europe, all of Australia, all of South Africa are expected to see decreases in the moisture on the land. So another way of saying that is increased aridity. And climate models have been projecting this for a very long time. And so this is why, you know, very early on in climate modeling, there was a projection of increased, for example, forest fire risk in the United States West and in the Mediterranean region, because immediately climate models started to say that this should be the pattern that we see. And in observations, this has emerged to some degree. This pattern is really kind of hitting these models hard with very high emissions, and then you're averaging over a bunch of models, and so it jumps out at you because you're kind of averaging out all of the noise. You're increasing the signal and decreasing the noise, and so observations are much noisier, but this pattern is kind of starting to emerge. Okay, so let's talk about that idea in terms of what's going on now in this study of the US Southwest. And we're going to look at observations and modeling here. So here's our LA Times headline again. This Western mega drought is the worst in a millennium. Study says it's being driven by climate change. So what they do in this study, I want to remind you of a graph I showed because they do something like almost identical to this. And this was the idea that, you know, you have some time down here, you have some weather climate variable. And so that there's just natural variability in the weather climate variable. So in this case, we're going to talk about like droughts or soil moisture or something that goes up and down just kind of randomly because of how there's just randomness in how, you know, storm systems move over a given location or not, and coincidences. But we can kind of use climate models to surmise that there's like some kind of underlying impact from climate change. And so then what you can do is you can kind of split, you can come up with a situation of what would this have looked like without increasing greenhouse gas concentrations. And so for this graph, it would be like the red is what we observed because we do have warming due to increased greenhouse gas concentrations. And then the black would be calculating what would have happened to this variable if there wasn't climate change, if you kind of subtracted that component of the change out. And so this is what's done with a lot of variables, and it's exactly what they do in the study to look at the impact from climate change on this current drought in the US Southwest. So this is basically our two components of the water cycle, their variability and the impact from climate change. So on the left is precipitation over the US Southwest from 1900 to 2020. And black is what we observe, observations. So it goes up and down and up and down, and it's random, and there's just a lot of variability. And the green line is what climate models say the component, like basically the contribution from greenhouse gas changes is. So it's almost nothing on precipitation, right? So this green line is just flat. So there's just this natural variability, and there's really not a trend that we think is being contributed from increased greenhouse gas concentrations. And you can kind of see that if you go back to this graph here of precipitation change under climate change, under global warming. This region that we're talking about encompasses an increase area and a decrease area, and there's not like a whole lot of agreement. So averaged over that area, we don't expect a change in total precipitation. So it's not really going to be that precipitation component that would be contributing to this drought situation. But on the right side is basically a measure of evaporation. So it's vapor pressure deficit is technically what this thing is, and what that is just a measure of like how much the atmosphere is able to essentially suck water out of the ground. But you can think of it as just evaporation. So we're not going to get we don't expect a change in precipitation from climate change, but we expect a change in evaporation from climate change. So this increased trend from the 1970s through 2020 is saying that that component of that increase in observations is due to increased greenhouse gas concentrations. So as it gets warmer, evaporation increases in this region, and precipitation does not necessarily change. So you're just going to always have this kind of random variability of precipitation. But then the other, going back to this graph, the other way of looking at that is you can like subtract out the climate change signal. And so then you have a series of observations in black, and then our calculated series of what it would have looked like without climate change, without increasing greenhouse gas concentrations. So the precipitation one looks basically the same. So with or without increasing greenhouse gas concentrations, they're basically the same. But the evaporation one, without increasing greenhouse gas concentrations, that's our green, then it would have kind of just stayed on this average line. But with increasing greenhouse gas concentrations, that's our black, then we have an increase in evaporation. So those are those, these are these two components, the input precipitation and the outgoing water evaporation. So then what does that look like in terms of what's happening to soil moisture? Like we know just from what I just showed you, if precipitation isn't increasing, but evaporation is increasing, then soil moisture should be decreasing due to climate change. And so that's what this shows you. This is summer soil moisture over the US Southwest. This is a kind of a processed statistical measure of that, but higher values are more moist and lower values are less moist. And so we see that we would have had this random variability no matter what, but by 2020, climate change has caused soil moisture to be about 19% lower or drier than it would have been otherwise without increasing greenhouse gas concentrations. So this is like one of the headline results from this study. This is showing, it's teasing out what is the impact from increasing greenhouse gas concentrations on this drought that we're experiencing now. But they talk about a mega drought. So they're talking about like a longer time scale. And so that's what this is like, basically the same graph, but adding on here these lines that are averages over 22 years. So the mega drought definition was it had to last 2 decades or more. And so this black line and then the two thick lines are looking at soil moisture, but averaged over 22 years. So like 10 years on each side of some central point. And so we see that we were kind of at a peak in the 1990s, and then since then it's been going down. And then this is the climate change impact on that 22-year average as 42%. So again, the way to interpret these are black is what we've seen. So this is our drought state currently. and green is where we would have been without climate change. So we would have been in a drought without climate change, but this is saying that it's 42% drier. So you can see that like here would be 0%. You're basically getting close to doubling the aridity here from that increase in evaporation, which causes the decrease in soil moisture. But the headline talked about worst in a millennium, but this only goes back to 1900. So this is like the observations that we're most sure about, that we have basically good records going back to 1900, and we can make educated guesses of how soil moisture varied over hundreds of years previous to that using tree rings. So anything that we think has a correlation with some other variable, we'll call a proxy of that thing. So tree ring widths are proxies for soil moisture. And so they can reconstruct this average soil moisture across the United States Southwest using tree rings. And what this graph is showing is from the year 800 now to 2022, and showing these what have been previous mega droughts. And this is showing this black line here is this exact same black line plotted on top of this data going back to the year 800. It now looks much spikier, much more dramatic, but that's only because you have a larger x-axis and actually a much smaller y-axis, right? Because this one goes from -1 to 1, and this one goes 3 to -3 to incorporate these interannual variability points. Okay, so this is showing if you draw a line back in time, right now, if we take all of the tree ring data at face value, right now we are the driest 22-year period in at least the past millennium plus. So it's like over 1,200 years. And then we can do the same thing of subtracting out the climate change contribution. And so this is what it would have looked like, according to these calculations, without climate change. So we would have still been in a drought, but we would not have been as severe as this drought in the late 1500s, or as severe as this drought, or as severe as this drought, or as severe as this drought. So climate change has caused this to be the most severe drought in this record. And there's your climate change contribution. I mean, it's good to me when I see this data, because it's saying that like we don't expect this to just plummet off the face of the planet. We expect that this natural variability will rebound, and despite the fact that we have this long-term drying trend in the background, which is only going to exacerbate all future droughts because of this increase in evaporation, it doesn't mean that we think that this actually is like quote unquote the new normal, that it's always going to be this dry in the US Southwest. And so hopefully this mega drought does end as other mega droughts have ended in the past, and we will be recovering to a more moist state that would be still drier than it would be without climate change. But that would help a lot, of course, with our fire situation and amount of water in our reservoirs. Okay, so understand the difference between meteorological droughts and hydrological agricultural droughts. So that was this idea. Meteorological droughts have to do with precipitation. That's what's coming in. That's what most people think about when we think about droughts, is just how much precipitation there is. But these other droughts tend to actually be what's more important for most uses of water. And those droughts take into account this evaporation part. So it's not just the precipitation in, it's also the evaporation out. And that's where we see more droughts under climate change. So that's the second part. Understand why hydrological or agricultural droughts should increase more than meteorological droughts as the climate warms. Well, overall precipitation should increase as it gets warmer. So meteorological droughts are not necessarily going to increase, although they will in some regions. But evaporation increases almost universally as it gets warmer. And so these types of droughts should encompass much more of the land surface than meteorological droughts. And then understand the contribution from increasing greenhouse gas concentrations to the current mega drought over the US Southwest. So that's kind of just a microcosm of the land in general, that we do not see increased greenhouse gas concentrations changing precipitation over the US Southwest, but we do see them changing evaporation and thus resulting in less soil moisture than we would get otherwise. And so that's what this is showing. Black is what we see, green is what it would have been like without increasing greenhouse gas concentrations.